Okay, welcome to another installment of Chemistry 3202 review. This lesson is just a short lesson based on one of the Science Technology Society issues dealing with energy. And it's going to be looking at sources of energy, alternate sources of energy, and where we can get the best fuel, I guess, to fuel society. So here we go. Dealt with on page 697 of your textbook if you want to have a little read there. Little picture here, of course, where we look at this guy, and we got this planet Earth here, and he looks awful upset, a little bit sick, I guess. And he's got this big toucan, global warming, and you can see embroidered in the toque is carbon dioxide. So that's the cloak of global warming there. So we're looking at energy issues, I guess, from the perspective of global warming and some of the other issues and concerns that come up here. Okay, here are the outcomes for this section, this lesson. And basically what I'm going to do here is simply go through some of the alternative forms of energy. You probably already know most of these, but what we're going to do is just look at each one and look at some of the pros and cons and see where we're going to take it from there. All right, so the very first source of energy that most of us are familiar with would be something like fossil fuels. We use fossil fuels all the time in our cars and heating our houses with oil and things like that. So these guys would be carbonized organic matter, so all kinds of diesel fuel, kerosene, gasoline, propane. These would all be the fossil fuels we're talking about. Non-renewable, I know you guys have heard that before. Once the oil is gone, it's gone. Once our reserves are all used up, we will not get any more oil, so for that reason we need to conserve. Number two, of course, I guess, or the third thing here is the fact that greenhouse gas emissions are very important here in the fact that not only are we going to get some carbon dioxide from the production of, or the combustion of gasoline and oils and petroleum products, but we also get acid rain production as well. So a few drawbacks here, and we all know, of course, these days that the price of oil is rising and it's getting more and more expensive to be using fossil fuels as an energy source. Not to mention that fossil fuels like the oil and the petroleum are the basis of many, many different types of petroleum products, as you learned in Chemistry 3202, from things like paint to vinyl siding to plastics to medicines to clothes, synthetic fibers, Kevlar, fiberglass. These things are all made from petroleum products. So if we're going to just burn all this material up in smoke to put in our vehicles and heating our homes and whatnot, that's a lot of material that's going to be gone. That we won't be able to convert to useful things that society may need or want in the future. There we go. The second form of energy, as we look in this picture up to the right here, we see solar panels here, and this is becoming more and more popular and more prevalent. Solar panels, of course, use the sun's energy to collect and convert to electrical energy, which is then stored in large batteries for the time when we need it. So they would be stored in big capacitors. Okay, becoming more and more prevalent. Practically, well, they don't burn any fuel, so therefore they're not producing any greenhouse gases, they're not producing any acid rain. Very clean, very efficient fuel. I guess one of the problems is, depending on how efficient the panels are in Newfoundland, especially around the coast where I live, it's foggy for 7/10 of the year, and the other 3/10 of the year it's generally cloudy. So some of these solar panels are very efficient. They don't need a whole lot of sunlight to be working, but they would probably be more efficient in areas where they have more sunlight and whatnot. So, you know, we'd have to weigh the pros and cons there, whether or not we would want to go through the expense of going through putting in solar panels, putting in all the batteries and capacitors, and the electrical technology that goes along with it is quite expensive. Okay, but once you got it, you got it. All right, it should last forever. The other thing here would be using hydrogen as a fuel source. And we know the big thing these days, of course, is we can do the electrolysis of water, which produces hydrogen and oxygen on two different electrodes here. And we can burn the hydrogen as a fuel source. And of course, when we burn hydrogen, we get water back. So there's no carbon dioxide being produced, and there's no acid rain being produced when we burn hydrogen as a fuel. We propel the space shuttles up in orbit using hydrogen and oxygen fuel. Right? We would ignite it and we get tremendous amounts of energy, and very clean energy because there's no carbon dioxide and there's no acid rain being produced here. The problem, of course, is in order to do the electrolysis of water we need electricity, and then the question is, well, where is the source of electricity coming from? Is it coming from a coal burning generating plant? If it is, then indirectly you're producing carbon dioxide. So, what is the source of the electricity there? Ideally, of course, if we could use solar energy to produce our electrolysis, then we'd be in business. Okay, another way of using hydrogen is using fuel cells. Okay, and you're going to look at fuel cells in a little more detail when we do electrochemistry. All right, it's actually a electrochemical reaction here where we harness the movement of electrons as hydrogen and oxygen are, as water is pushed through the fuel cell. All right, and in that way, the electrochemical reaction happens inside, much like a battery. It produces electricity, and the electricity, of course, can run motors, light bulbs, electric devices of any kind. There we go. So again, very clean, no carbon dioxide, no sulfur dioxides, no acid rain, no global warming. Okay, number 3 here on the top, we have a little gas pump on the side, but is it really a gas pump? Well, it looks like a gas pump, but what it is, it's an ethanol outlet here where ethanol is being used as a fuel. So with ethanol, it's like a flex fuel vehicle. Some of you guys may have vehicles at home that have a flex fuel stamp stuck on the side of the car. And flex fuel is capable of burning gasoline, but also mixtures of gasoline and ethanol. And it's a much cleaner fuel. It's renewable because what we do here in order to get the alcohol, ethanol, is they actually ferment grains like corn and wheat and things like that. Now, one of the problems with this is people are saying that the costs of corn and wheat and things like that is causing food prices to increase, because rather than the food being entered into the food market for human consumption, what's happening is the grain and alcohol is fetching a larger price as it's fermented to produce ethanol for burning in cars and whatnot. So for that reason, there's a large demand on grains, which is causing food prices to increase. All right. So what you find is that every time you come up with a solution to one of your problems, it creates another problem, and so the cycle continues. Right. So that's an issue here. So they use the ethanol for combustion. Of course, it burns very quickly, very efficiently. The amount of carbon dioxide is not as much as you would get from burning fossil fuels. And you wouldn't get any sulfur dioxide because there's no sulfur in the ethanol. The sulfur in petroleum products is embedded in the coal and in the gasoline. They try to clean it off when they do the petroleum refining. But you're always going to have a small amount of sulfur left in the gasoline and in the coal. And when you burn it, of course, the sulfur burns as sulfur dioxide. When we burn ethanol, of course, there is no sulfur there, so we don't get any acid rain from this. But we do get some carbon dioxide, but not as much as you would if you burn straight gasoline. There we go. Okay. The fourth one, of course, is mechanical energy, and things like wind energy, tidal energy, hydroelectric dams, and whatnot. And what's happening, of course, it's harnessing the energy of the wind or the tide or rivers to turn turbines, which then generates electricity from the turning of the turbines. Again, good because there's no greenhouse gases, there's no acid rain. Hydroelectric, flooding, right? You got to dam up an area. They're very expensive. They're great big projects. We know that there's a big project that's proposed for Labrador hopefully in the next few years, or depending on what side of that you sit on. Very expensive projects to build that up, but once it's built, of course, it lasts for years and years and years and years. And there's no expenses in the upkeep, so you get cheap fuel in the long run, or cheap electricity in the long run. All right. And of course, these wind farms are popping up all over the place where we're harnessing the wind's energy. Okay, and I think there's a wind farm on the Burin Peninsula, down by Burin, down that way, Marystown area. I think there's a small wind farm. There's a few windmills down there that are generating electricity that's being fed into the Newfoundland grid. There we go. Nuclear energy. Now, this one here is receiving lots of attention these days because of Fukushima in Japan. We've had several meltdowns, 3 big ones, I guess, over the last 30 years or so. Fukushima, the most recent one. And generally, the idea behind nuclear energy is the idea that a very small piece of uranium or other radioactive material, very, very tiny piece, about the size of an eraser, is equivalent to the same amount of heat that, say, a dump truck load of coal would be able to produce. So a very, very tiny amount of uranium is able to produce an enormous amount of energy over a long period of time. And this enormous amount of energy that comes from the radioactive uranium or other radioactive material that they might use is simply used to boil water, which creates steam, and then the steam would turn the turbine. So the principle behind how the nuclear reactor works is very simple, right? You're simply boiling water. So the idea behind it is that, in a sense, it's a really clean energy. The amount of waste material is minimal compared to the amount of waste with burning coal or gasoline. We don't get any carbon dioxide, carbon monoxide. We don't get any nitrogen monoxides or dioxides. And we don't get any sulfur dioxide, so we don't get acid rain. One of the problems, of course, though, is if it gets out of control and weird things start to happen, is that you get the meltdown, and then it can be a disaster, as in the area of Fukushima. One of the things about nuclear fuel, though, is that because you're such a small quantity of nuclear material that's required to produce such an enormous amount of energy, it's too clean and too valuable for countries to simply say we're not going to do the nuclear thing. What they have to be able to do is do the nuclear thing better, right? And here's basically the nuclear reactor. And what's happening here is there's the nuclear core is within this great big concrete structure. And it's cooled by cooling water, of course, and this very hot water is producing the steam, and then the steam is going to be using to turn the turbines, which creates the electricity. Now you can see it's protected because you've got several loops of cooling, where the inner core never really comes in direct contact with the outside world because it's isolated by several different loops. All right, so here's the inner core, and this energy, this fluid would boil the water, but it never comes in contact because this fluid never mixes with this water here. All right, so technically speaking, they keep it cooled by using external loops. All right, don't want to get into it, but anyways, you get the idea. Okay, there's what happens when we get a big meltdown. Of course, Fukushima never happened like that, did it? You don't get a great big explosion. What happens is the nuclear core overheats, and then as it begins to burn, all the smoke and residue that rises from the flame is radioactive. All right, in the surrounding area, as the smoke begins to settle, it settles on the ground, and of course then you get radioactive fallout from that. So it's not going to be a great big explosion like you would see with a nuclear bomb. But it would be a meltdown where the whole core would start to catch on fire, and what happens is it overheats, and then it's very difficult to cool down the nuclear reaction. Okay, a couple important reactions here that we want to talk about. Photosynthesis. All right, we all know what photosynthesis is. That's what plants do to take carbon dioxide and make glucose. That's an endothermic process. Energy is absorbed, right? Because the sun is coming down, the plant is absorbing energy. Fermentation, when we want to make ethanol to burn, or if someone's making wine or whiskey or beer or something like that, yeast would feed off the starch and glucose that the plants have stored the energy from the sun, and then the yeast would convert this to ethanol and a little bit of carbon dioxide. Okay, but what we're saying is this carbon dioxide that's produced here is consumed by the plant, so it's a good system when you think about it. Respiration is what we do when we eat the plant's food, and we notice that respiration is the reverse of photosynthesis. Photosynthesis produces glucose and oxygen and absorbs 28 kilojoules per mole, 2800, sorry. This guy down here, when we consume sugar products, glucose and starch and whatnot, we breathe in oxygen, we burn this for fuel, we produce carbon dioxide and water vapor, and the energy is the exact same value, except now we're releasing it because we're using the energy for bodily functions, moving, muscle contractions, etc. Okay, here's a comparison of molar heats then of the different types of energies that we can use. Now we've already seen this, so I'm going to go down through this rather quickly. We're looking at this idea of saying phase changes, physical changes or phase changes. They don't involve a tremendous amount of energy. Melting ice, we can do that in our hand, right? Boiling water, put it on the kettle on the stove, we can boil water real easy. Doesn't take a whole lot of energy. And we notice that we're not really breaking anything apart. All we're doing is disrupting the London dispersion, dipole-dipole, and hydrogen bonding. All right, so there's no covalent bonds being broken. So no new substances being formed, simply a change of state in each case. Small amounts of energy because the forces holding together solid water and liquid water are relatively weak. It's only intermolecular forces of attraction, so relatively weak. We compare that then to chemical changes, and this is where we're going to start breaking and forming new covalent bonds. And we've seen this with Hess's law and bond energy calculations and things like that. When we start breaking covalent bonds and forming new covalent bonds, there's going to be a much more energy involved. So in this case, the combustion of coal releases a tremendous amount of energy. It's a negative 3,900, which is, 100 times more energy than it would take to boil water. So the burning of coal releases 100 times more energy than coal. So a tremendous amount of energy stored in these bonds, these covalent bonds. And finally, of course, uranium or radioactive reactions. These guys are mammoth in the amount of energy that's stored in the nucleus. And how do we know we're talking about the nucleus? Well, as we said before, anytime you see this isotope notation, you're looking at changes to the nucleus. Uranium with 92 protons was split to produce a polonium with 90 protons and an alpha particle helium here with 2 protons. So what we've done here is we've split the nucleus, and in doing so we've released the tremendous monstrosity of energy that's stored in the nucleus. And this is plus 2.1 times 10 to the 10. That's a 2 with 10 zeros after it. That's how many kilojoules of energy are released. 21 billion kilojoules per mole. Compare that to carbon, not even in the same ballpark. Right? Tremendous amount of energy in nuclear changes. And the reason that's so important, of course, is you can use very little of uranium to get an enormous amount of energy. Very small quantities of uranium is required. And there we go. So that's it on alternative that's it. Take 3. That's it for alternative sources of energy. Here we go. Okay, so again, have a look in your textbook, and they may ask you some multiple choice and whatnot on this. Read the material and be familiar with it. Okay, see ya.